Hi guys, grade 11s finally. Grade 12s, hope you're also tuning in because you know a little bit of revision never hurt anyone. This is Bruce, and
Hi.
Bruce will be doing grade 11 with us today, and he's going to chat to us about what he's going to be teaching us.
Chemical bonding.
I know, and
Yeah.
apparently it's going to be quite an exciting one.
Chemical bonding, very important for grade 11s, one of the foundation modules that you have in your chemistry. So you guys tune in and keep watching, eh? Lots of questions, please. That would be great.
Guys, chemical bonding, you guys should know what Facebook and Twitter is by now. www.facebook.com/learnextra, that's XTRA. Also chat to us on Twitter @learnextra. Any questions you have, I'll let old Bruce know over here,
Cool.
and he will help us out. So, guys, see you straight after the break. Guys, we are back and we are ready, and are we excited? Grade 11s, we hope that you're joining in. I'm excited. I know that I'm going to be learning lots today. So guys, help me out, make my life easier and send me questions on the topic that we're talking about. And that is chemical bonding.
Chemical bonding.
Yeah. So, Bruce, take it away.
Right, thanks Indiana. And guys, welcome to the show. Great to have you guys with us, grade 11 students. And as Indiana said, we're going to be spending some time looking at chemical bonding. Now, in grade 10, you probably would have done some form of chemical bonding, would have introduced the topic. But what I want to do today is actually start taking it down to a little bit more of a deeper level. And we just need to understand there are quite a few important concepts out there that really are important when it comes to understanding the chemical bonding models. Now, a lot of people turn around and say, what do we mean by a chemical bonding model? Well, I'll talk about that a little bit later. But to understand what a chemical bond is, we have to go back to grade 10 a little bit. We need to go back and remind ourselves and revise a little bit about electron structures and the electron structures and how electrons are arranged in an atom. And you'll probably come across, or remember coming across, something called an Aufbau diagram. Okay, I'll just write it up there for you. And you might have heard of it as an energy level diagram. Okay, and the important thing about an Aufbau diagram or an energy level diagram is that it allows us to explain and show and illustrate the structure of electrons around the nucleus within the atom. Now guys, you must be aware that no one has ever seen this. This is something that comes from mathematical derivations, and all these clever guys who went out there and they actually went and did huge mathematical calculations, and they came up with these fantastic ideas. And these ideas are not that old. If we think about it now, we're 2012. A lot of these ideas came out in the 1920s. And if you think about it, do some simple maths, that's round about 70 to 80 years ago. So it's actually very, very new. And guys, it actually works. Over 70, 80 years, no one has actually come up with a better understanding of how electrons are arranged. So therefore, we accept it, we do it, it explains it to us, and it makes our life very, very easy. But I just want to quickly show you guys, just to remind you about electron structures. And I'm going to take a very simple example. I'm going to take oxygen, okay? And if I take oxygen here, and we all know that oxygen's got the symbol O, and we all know that it's got a mass number of 16, okay? Now, in fact, I do apologize. I've just given you the mass number. I want to give you the atomic number, and the atomic number is 8. Now, atomic number, what does atomic number actually indicate to us? Well, the atomic number indicates the number of protons in the nucleus. Okay, that's what makes oxygen, oxygen. However, for the atom of oxygen, it also indicates the number of electrons that are now orbiting around this nucleus. Okay, Tracy in the grade 10 lesson earlier spoke about Rutherford and developing the nuclear model where the electrons orbit around. She spoke about Niels Bohr and things like that. Those were all people, great scientists, who contributed to these ideas. But oxygen itself, with an atomic number of 8, with 8 electrons, then the modern electron structure was to say, how do we arrange these? How are these electrons arranged around the nucleus? So what I'm going to do, I'm just going to basically extend the page a little bit, and we're going to do our energy level diagram. Let's extend a little bit. F bar, here we go. And you'll remember that we looked at energy levels and we looked at orbitals. And we looked at energy level 1, where you had an orbital which you called the s orbital. And we separated the s orbital with energy level 2. And we said it had an s and a p orbital. And we drew them like this. There are Aufbau structures. And we could see now that the s orbitals were much smaller than the p orbitals within that energy level. Now, if we have to remind ourselves what an energy level actually is, it is, shall I rather say, not was, it is a band of energy. And that band of energy, and I'm going to draw it just over here quickly for you guys. If this is my nucleus over here, these energy levels were bands that were placed in a sort of circular notation. And if I had to color it in like this, that would be energy level number 1. And it would encompass this entire range. I'll just get some colors here for you. And there we go. An entire range of energy. And in there, the electron could move around. I'll just dot it like this. And anywhere inside that band, all the way around. Okay. In other words, it had a free path to orbit around that nucleus. Okay. Then we went to energy level number 2. Now, energy level number 2 could have more electrons. There were only a maximum of 2 electrons could fit into energy level number 1. The other electrons, the rest of the electrons, basically could fit into energy level number 2. But how many could go in there? Well, there we could only find 8 electrons. Okay? And the 8 electrons were found in this band. Okay, so let's go back. And I'll just sort of make a little bit of a different diagram for you. There it is. 8 electrons, but the 8 electrons were found in an s and p orbitals. Okay, the s and the p orbitals. Important thing about s orbitals, a maximum of 2 electrons, p orbitals, a maximum of 6 electrons. 2 plus 6 equals 8. And that's why energy level 2 was able to have a maximum of 8 electrons. So now, let's have a look at the electron structure, electron configuration of oxygen. Well, we said now that oxygen has got an atomic number of 8, which means we've got a total of 8 electrons which we must arrange around that nucleus. How do we do it? Well, remember, electrons are always found in pairs, okay? And we indicate them by little arrows, okay? One arrow up, one arrow down, to counteract the repulsive forces, to have opposite spins. Stuff that you should have done in grade 10. So there were 2 in the 1s orbital. Then we go to energy level 2. We put 2 electrons into the 2s orbital. And then the remaining electrons end up, whoops, get this pen right, end up in the p orbital. So we go 1, 2, 3, 4, 5, 6, and 7. And can you see now that we've got the 8th electron is over here, which leaves 2 electrons unpaired. Now, guys, what is the significance of having unpaired electrons? Well, the significance of having unpaired electrons is that atoms are not in their most stable energetic state. Yes, protons and electrons are equal. The atom is neutral. That's great. However, the atoms are not in their most stable energy state, because atoms are only stable when you have filled outermost energy levels. And as you can see over here, over there, and over there, can you see now we have got 2 electrons short. We have got what we call unpaired electrons. Now, what is the oxygen atom going to try and do? It's going to try and get itself electrons. And this is where chemical bonding takes place. So in other words, a chemical bond takes place so that atoms can now attain the electrons to fill these outermost energy levels. And once you fill that outermost energy level, you are in a stable structure. Okay. So, for example, let me just extend the page again. Here we go, a little bit more. Here we go. If we take oxygen. Now, you should have learned that in grade 10, oxygen has got a chemical formula of O2. It's what we call, and let's go back to my white ink over here, it's what we call a diatomic molecule. Okay, it's a diatomic molecule. All right, diatomic, di means two atoms. Okay, atomic, atoms, diatomic, two atoms. Okay, that make up the molecule. But oxygen, okay, the reason why it has to exist as a diatomic molecule is because now each oxygen atom that is bonded together must have the filled outermost energy levels. In other words, a completely filled outermost energy shell. Okay, so atoms bond, should I rather say, atoms bond so that they can fill these outermost energy levels. They now achieve that most stable energy state, and once they've got that most stable energy state, then they can exist in nature, basically, in the environment. As you know, that's exactly what we breathe. We breathe oxygen. We breathe O2. We don't breathe O, okay, because O can't exist. O2 can exist. And just like we have other molecules that you'll recognize, H2O, water, okay? We all drink water to keep ourselves basically alive and hydrated. H2O, two hydrogens to one oxygen. There's a chemical bond between hydrogen and oxygen, again, achieving the most stable energy state. The water molecule is going to be stable. If we take another one, which is also a diatomic, one of our diatomic gases, nitrogen. Okay, we should have learned probably even down in grade 8 and grade 9 that nitrogen makes up 79% of the Earth's atmosphere. Oxygen only makes around about 20%, plus minus, and then 1% of the Earth's atmosphere is made up of all other types of gases. So guys, we are always talking about chemical bonds, bonding and that sort of stuff, making the atom stable and therefore the molecules going to be stable as well. Okay, but the big question is how does this all happen? And this is what we are going to actually spend a little bit of time having a look at and making sure that we do understand it, because there are quite a few little intricate things that we need to look at. And one of them is to speak more about this energy that's now present in the system and how do we get this most stable energy state. Okay, so what I want to do is show you exactly now, through a little simulation that I'm going to do on the board itself, how atoms actually achieve this. Okay, so
I'm sure the mindset is going to be very excited about that.
Well, we hope so.
Yeah.
So I'm just going to extend the page again. And yeah, because it's really important for the grade 11s to actually understand this.
Yeah.
Because the one thing about putting atoms together is, well, it's quite easy. We can just plug them together and you know what? And it's just a case of just copying it out of a textbook. But the actual understanding as to why this all happens, this is what the crucial point is. And this is what, if you can have this knowledge and take this knowledge into your tests and exams, well, then we're going to be in a fantastic place to actually understand it. Okay, so let me quickly show you what's going to happen. And I'm going to take a very, very simple molecule, and it's the simplest molecule. I just want to get rid of this guy because he's sort of in the way there. And we're going to look at another diatomic molecule, which is hydrogen. Now, the reason I've chosen hydrogen is because hydrogen is such a simple atom. Okay, as you know, hydrogen has got a nucleus, okay, and it's only got one electron which is going to orbit around that nucleus, okay? So I'm going to just draw that electron over there in green, okay? Now, what's going to happen if we have a look, if we have a look, let's go back there. If we have a look at hydrogen, it's got one electron. Remember, guys, it needs to achieve its most stable energy state. Therefore, it's going to now try and fill its outermost energy level. Okay, energy level 1 can take a maximum of 2 electrons. So therefore, hydrogen is looking for one more electron to actually fill it. If I did the energy level diagram, it will just simply be 1s, and I'll do a nice color for you. I would put in 1 electron like that. So we can see now over here that we are short of 1 electron in that position. Okay, so that arrow didn't come up very well, did it? There we go, much better. We are short of 1 electron. So, where's it going to find another electron? Well, if it can find another hydrogen atom, let's do that. Let's find another hydrogen atom. Okay, there's the nucleus, and there is now the energy level number 1, and the 1 electron in that hydrogen atom, maybe something can happen, and these electrons can start to pair up. Okay, in other words, we can start forming a chemical bond. But there are a couple of things that have to happen for this whole thing, this whole process to take place. And what I've tried to show here is now these 2 hydrogen atoms in proximity to each other. In other words, quite close to each other. Now, what we must remember is that we've got a nucleus, okay, and what do we know about the nucleus? The nucleus contains protons. What are the charge on the protons? The protons are positive. So I'm going to just mark in there, positive for the nucleus. And what do we know about the electrons? Well, we know that the electrons are negative. So as these, as these atoms approach each other, we are now going to have interactions between positive charge, the positively charged nucleus, and the negatively charged electrons. Okay, so what's going to happen now, okay, now let's get a nice fancy color over here. In fact, I'm going to go with a purple dotted line here. We are going to start getting attractive forces between the protons of one nucleus, of the one atom, and the electron out in the outermost orbital of the other. So we're going to have an attractive force, and can you see now that we're going to have attractive forces like that? Okay, so what's going to happen is that the atoms are going to be pulled together by these attractive forces between the positively charged nucleus and the negatively charged electrons. But if you're quite sharp and you're watching very, very carefully here, what actually also is going to happen, can you see now we've got like charges? Like charges. Now, what do we know about like charges? Like charges are going to repel each other. So what's going to happen now, okay, is that, and I'll probably just have to do this one in red, I think. Okay, let's get rid of that. Is that we are now going to have repulsive forces. So what I'm drawing in red here are going to be repulsive forces. And these repulsive forces will start becoming significant as the atoms get closer and closer and closer together. Okay. Now, once they get closer and closer and closer together, and the repulsive forces start becoming significant, we now start talking about balancing forces. The repulsive forces and the attractive forces balancing each other out. And once we get this balancing out, then we are able to create what is known as a chemical bond. Okay, it's the balancing out of these forces. Okay, what happens to the electrons? Well, the electrons now actually end up being shared. Now, how does this work? Let me show you quickly. I'm going to draw it like this. Okay, so there's the one atom. Okay, there's the one hydrogen atom, like that. What happens now is when they come closer together, the outermost orbitals actually overlap. And what we now get is what is called an orbital overlap structure. Okay, I'll just write it down here. We've got an overlap, an orbital overlap structure. Okay? Now, when the atoms are able to overlap, we have got balance between the repulsive and the attractive forces that exist within the actual atoms themselves, or between the atoms themselves. Okay? What happens to these electrons? Well, in that region of overlap, the electrons end up getting shared between them. Okay? And what happens when we get them shared is that, I'll just write it here, we have sharing of electrons. There's a share of electrons, okay? Share of electrons taking place at that point. If they are shared, then can you see now that at some stage this atom will have 2 electrons and this atom will have 2 electrons. Okay? And therefore we have satisfied the criteria of having the outermost energy levels being filled. and therefore we are in the most stable state. And this is how the hydrogen molecule is formed. Okay, there it is, the hydrogen molecule. That is how the hydrogen molecule is formed. It's basically formed through this overlap of the outermost electrons, balancing of the attractive and repulsive forces between the nucleus and the outermost electrons, okay, and obviously between the electrons and the nucleus themselves, and that represents a chemical bond. Okay. Now,
Bruce,
what I want to do, sorry, Indiana, jump in. Yes, jump in.
Before we carry on, I wanted to know, actually, just wait. Carry on.
All right. But I think we're going to probably take a little break now because
Yes.
I want to talk a little bit about energetics. I've given you the basics now of how we form this bond. There are a few other things that we need to look at. We need to look at the energy. Okay, how do we stabilize? We said this is the most stable part, the most stable configuration by having this molecular structure. Okay, the electrons are shared, so in other words, outermost energy levels are filled. Okay, so both atoms are saying that's great, we're absolutely happy now, but there's something quite important that I need to show you on a graph to show you exactly how the energy works within the molecule, and then we're going to introduce a concept called bond length. And that bond length is going to now define the distance that the actual chemical bond has within that molecule. Okay, so shall we take a little break?
Before we go to break,
Okay.
quick question.
Oh, it's a question.
Yeah,
Cool.
quick question,
Yeah.
which I love, guys. What I love the most, and this question is from Lorato.
Lorato.
And Lorato is speaking about the exact question we're talking about, so it's relevant. Guys, please write in with questions you have, but stuff that Bruce is actually talking about. I mean, there's no use us talking about this or that, which, you know, we're going to cover those subjects as time goes on. So here you go, Bruce. Lorato wants to know, what will happen if the repulsive forces repel each other? If it doesn't make sense.
I think I know what
Yeah.
Lorato is trying to say. He's trying to say now, what happens if we don't have a balance? Okay, Lorato, I hope this is correct. If not, please just get back to us on our, is it Facebook or Twitter or whatever?
Facebook.
On
Yeah.
Facebook, get back to us. But what will happen, okay, here we have now the balance between the attractive and repulsive forces. If the repulsive forces get bigger, the only way they can get bigger is if we actually take these two atoms and we sort of force them together. Then you're not going to have a balance because then the two nuclei are going to be too close together, okay? And therefore you're going to have a domination of the repulsive forces. As soon as that happens, the energy in the system goes straight up. And if the energy in the system goes straight up, Indiana, what happens? The system is not stable and the whole thing is going to break down. But luckily, guys, we don't have huge people coming in trying to push these molecules together. Nature's a very clever thing. Nature works this all out for herself, okay? And she basically allows for the most stable state to remain. And therefore, you won't have the repulsive forces being bigger or dominating or sort of overriding anything else. Mother Nature takes care of a lot of things for us.
Fantastic. And
Okay.
we've got another one, mine as well, because they obviously heard my advice. What about the energy changes during bond formation? And that's from Tapiwa.
Okay, now energy changes during bond formation. Okay, and that I think you're talking about from a chemical reaction point of view. It's very important, and I'm going to talk about it a little bit later today. Well, I hope we're going to have time to talk about it. Is that the chemical bond itself, there's energy within that bond. Okay? Now, when a chemical reaction occurs, then we're going to have to break bonds and make new ones. Okay? It's a very important part of all chemistry. Now, when we break a bond, we need to put energy into a system to break the bond. When the new bond forms, energy is released. So what we have is what we call as a bond-breaking, bond-making type of setup. Okay, and this bond-breaking, bond-making type of setup then allows for the system to either release energy, which I think a lot of people call, and you guys will know, as an exothermic reaction, or if there isn't enough energy released on the bond formation, then the system pulls energy in. In other words, you need energy to keep it going, and we call that an endothermic reaction. Okay, but those type of calculations we are going to look at a bit later, but it is important that you have touched on something, that a chemical bond, there's energy in the bond, and if that bond has to break, then we need energy to break that bond, because everything now is held together in the lowest energy configuration. Therefore, it doesn't want to break by itself. It's saying, I'm cool, I'm in my most stable state, and therefore to break me, I've got to put energy in. Then the whole system undergoes what is called a chemical reaction. Okay, that's about the best.
That's fantastic. Bruce, are you okay? I've got 3 more questions. You want to go for a break, or are you happy to continue?
I'm quite happy. If you're quite happy, I can keep going. Give me the questions. Let's go.
Producer, should we take a break? Oh, she says, please. You know, producer, really. So, guys, producer has spoken. We're going to take a break. You know what? We've got 3 more questions. I'm going to ask Bruce. Anele, your question. Lando, your question. And Sipho, your question. So we'll see you guys back after the break. Welcome back, guys. We're having such fun. Bruce is in today, and he's keeping us all very entertained, and he's making physical science for grade 11s fun. Guys, thanks so much for writing on the page. It's been fantastic. We want you to write even more. And we're going to try and get through everything we can today. If we don't get your questions on the Facebook page, not to stress. We do have a team that sits and go through all the answers and all the questions, and they try and get back to you within 48 hours. And we're going to try and work through everything as fast as we can. We've got 2 questions, actually 3 questions, but Seaport wants to know, what is the Lewis structure? Guys, we're going to go through that at a later stage, maybe next week or the week after, but we are going to get there. Shall we get on to it, Bruce?
Oh, you've got those other
Yes,
questions.
are you ready?
Ask those other questions, then I'll get on to the energetics a bit later.
Yes.
I think while questions are coming in, let's keep everyone entertained.
Fantastic. Okay,
Cool.
This is Anele. Anele wants to know,
Right.
yeah, this is from Facebook.
Cool.
Is it possible for hydrogen to bond with elements that are from other groups?
Absolutely. Hydrogen is able to bond, it'll look for anything that is prepared to give it that electron to fill up its outermost energy level. Okay, so let's take an example. In fact, Tracy left this periodic table over here, and let's just have a look and see what we can interpret. There's hydrogen over here, okay, and it's stuck in group 1 for a very important reason. Now, we speak about the electrons in the outermost energy levels. Now, there's a certain name associated with electrons in the outermost energy level, and they're called the valence electrons. Okay, it's a word that might have been used in grade 10. It's certainly a word that's very important from a grade 11 point of view. So when we look at the periodic table, and a lot of people have spent time in grade 10 looking at the periodic table and maybe have revised it now in grade 11, is that our groups, our vertical columns, tell us the number of valence electrons. So if we look at group 1, for example, okay, group 1 have all got 1 electron in it in their highest energy levels. They're called the valence electrons, okay? So hydrogen, lithium, sodium, potassium, rubidium, etc., etc., okay? Then we go to group 2, beryllium, magnesium, calcium. They've got 2 valence electrons, okay? Let's skip the transition metals. Let's go across to group 3, okay? 3 valence electrons, etc., until we get to the very end, which is group 8, which have got a completely filled outermost energy level. They are known as the noble gases, or the inert gases. Why are they called noble and inert? Because they won't react because their outermost energy levels are full. So, if I'm looking at hydrogen, okay, and remember guys, a lot of people ask the question, how come hydrogen, because it's not a metal, hydrogen's associated with lithium, sodium, potassium in the same group? Well guys, it's got nothing to do with metal or non-metal. It's got to do with valence electron structure. And hydrogen's put there because it's got 1 valence electron. Okay. Now, if it needs 1 electron to fill its outermost energy level, then maybe it can come up with some sort of agreement, some sort of understanding, and please I've put this in inverted commas, that maybe there's another atom out there that needs 1 electron to fill its outermost energy level. And, well, if we go all the way across to group 7, okay, group 7 actually needs, well, those atoms need 1 electron. Okay, fluorine needs 1. Why? Because if it gains 1, or receives an electron, it's going to now have the filled energy level, which is going to be associated with group 8, like with neon. Chlorine will receive 1 more electron. It will then fill its outermost energy level, and it will have the same number of electrons as argon. So yes, to answer that question, hydrogen will definitely look to bond with elements outside of or let's say other atoms from other groups. Let me show you guys quickly, and I'll go back to the board. Let's take hydrogen. Okay, there's hydrogen. Whoops, let's get our pen back. All right, there's hydrogen, there's the nucleus. Okay, and here's the electron. Okay, over there. Now, let's look at something like fluorine. Okay, now, how many electrons does fluorine have? Well, if we look at fluorine, it's in group 7. Let's go back to our periodic table quickly. There it is. It's in group 7. Okay, there are a total of 9 electrons, but remember, guys, group 7 means it's got 7 valence electrons. Okay, so let's now quickly go and draw that. Okay, so it's going to be a bit of a bigger, let's get my pen back, let's get it over here. It's going to be a bit of a bigger atom than hydrogen. Okay, and it's going to have 7 valence electrons. Now, I'll do them in a different color. It's going to have 1, 2, 3, 4, 5, 6, and 7. Okay, and there's the nucleus in the middle. Okay, now I've drawn them out like that. That should be fairly familiar to you in terms of the energy level diagrams, where you've got, there are the electrons in the 2s orbital. We always put them at the 12 o'clock position, just for convenience sake. These electrons here are going to be the electrons in the p orbitals, okay, and you're going to have a 2p over there, you're going to have electrons in the 2p there, and can you see now, that's also in the 2p, but there's only 1 electron, guys, okay, which means then he is unpaired, and there are 7 around here, they're looking for 8, all right, what can come along? Well, hydrogen's got 1 electron. So if that electron could somehow get involved here, then the fluorine atom, I'll just put F for fluorine over there, the fluorine atom will have its 8 electrons. Okay? Hydrogen, however, has got 1 electron, it's looking for 2, because remember, the energy level 1 can only take 2 electrons. So if it can strike a deal with the fluorine, guess what can happen? This electron can maybe be shared with that electron over there to give 2 electrons to the hydrogen, and that electron here can maybe be shared with the fluorine to give fluorine its 8 electrons. So there now we can start getting a chemical bond taking place. So let me just pull this down a little bit and let's see what's going to happen. Right, so they will approach each other. Remember, guys, they're approaching each other. There's the nucleus. Okay, and what will happen is the outermost orbitals will overlap like that. The electron from the hydrogen, which was the green one, is going to be shared with that unpaired electron from the fluorine. There now, these guys don't get involved. Remember, they just stay there because they're already, there's the nucleus. They are already paired, so there's no problem. There now is our shared electron pair. Okay, and once we've got a shared electron pair, let's just put our writing there's hydrogen. Okay, here's fluorine. Okay, let me get this guy out the way because he's now, oh goodness gracious, look what I've done. Let's bring him back. Beautiful. Join them up there. There's hydrogen and fluorine together, and guess what? We produce hydrogen fluoride. There now is another molecule. Okay. The molecule is in its most stable state. Why? Because the sharing is allowed both atoms in that molecule to have a completely full outermost energy level. And therefore, we're in our most stable state. And that's basically answering that question. So, yes, hydrogen will look for anything that will allow it to get that extra electron to stabilize it. I think that answers
Yeah,
that question.
yeah, that's an incredible answer.
Cool.
I think you may have even answered a few other people's
All right,
questions
let's
along the
see
way.
what they've got.
No, but I think you've actually answered a whole bunch of them. I've been trying to he's
Okay,
answering them.
okay.
Okay, hold on, let me have a look. Oh, you see now. Talking about valence and valency, I think
Valence and valence. Okay, valence
yeah, what's
and
the
valency.
difference?
All
What's
right.
the difference?
That's a great question. That really is a good question. I haven't really alluded to valency, although let me just extend the page a little bit. I will come and chat to you about it to get these
But you know,
smudges out the way.
Bruce, do you know what I love about this question? Is that Lando asked the question and Sizwe has already answered it on the page for her. And for me, that's what a mindset is about. It's about these learners that are on the page and there's something they don't understand and they don't wait for a teacher. They just get in and they see that somebody's struggling and then they answer them. Guys, I love that. I love that. Sizwe, thank you. Thank you so much.
No, that's great. And guys, you've got interactive social networking sites that are at your fingertips with Facebook and Twitter and all that sort of stuff. Guys, use them
to help
Use
you,
them.
to
Set up
help
study
you.
groups.
Yeah.
Set up little study groups. I know people have got BBMs and all that sort of stuff, and I know you sort of communicate, but Facebook and Twitter is going to allow you to do exactly the same thing and probably be instantaneously interactive, and guys can talk online.
But that's exactly what
And
we're
that's
doing
it.
here, Bruce, and that's what I love.
That's cool.
Like, I mean, even the grade 12s of last year, they set up study groups online that
Cool.
anyone could join.
There we go.
That's exactly what we're kind of about, except we've got the live show, but that doesn't stop you guys from starting your own groups and chatting and helping each other out.
Fantastic. Yeah, awesome.
That's it.
Valence and valency.
Yes.
Right, let's have a chat about that. So who sent the question in?
That was Lando.
Lando. Okay, so Lando, hope you're watching. Let's have a look. We go back to the periodic table over here, and I spoke about these groups, okay? And I introduced them, and I said that they represent the number of electrons in that outermost energy level, okay? They are called the valence electrons. So, for example, if I go to group 7, for example, over here, group 7 have got 7 valence electrons, okay? Now, the question is, in fact, what the question is, we actually sort of looked at it when I did that example of hydrogen fluoride. How many electrons does fluorine need to fill that outermost energy shell? Well, we can see now it just needs 1. It needs 1 to have a completely filled energy level, to have the same electron structure as neon on the periodic table. So therefore, it needs to gain 1 electron somehow, okay? If it shares, it shares. That's great. But it needs to gain that electron. That electron needs to satisfy the energy requirements, the lowest energy configuration, the lowest energy position of fluorine. All right. Now, that 1 electron is called the valency. So if fluorine has got 7 valence electrons, and it needs 1 electron to fill that outermost energy level, then we say fluorine has a valency of 1. It needs 1 electron. Okay, let's look at another example. Let's take oxygen right next door. Okay, oxygen is in group 6. Oxygen in group 6 now has 6 valence electrons. How many electrons does it need to fill that outermost energy level, hence attaining the most stable energy state? Well, it's going to need 1, 2. Can you see now? 1 hop, 2 hops to get to neon. Remember, group 8 is full. So therefore, although oxygen has got 6 valence electrons, its valency is 2 because it needs 2 electrons. Okay, so there's the difference between valence electrons and valency. And guys, not just Lando, but everyone who's out there, be careful. They are very similar sounding words. And Indiana, that's where a lot of grade 11 pupils get confused because it sounds so familiar, it's so similar. And they just get mixed up and muddled up. And guys, just make sure that whatever textbook you're using or notes that your teacher's given you, whatever, that you take your highlighting pen, highlight those 2 words, those 2 definitions, because you don't want to muddle them up. And I know, and take it from a lot of experience, teachers like to test the difference between valence electrons and valency. Okay, Another quick example, I've spoken about these guys, but what about these chaps over here? How does valence electrons and valency work here? Well, let's take group 2. Group 2 has got 2 valence electrons, as we know. The group number tells us that. Now, there, if we look at, for example, let's take magnesium. Magnesium sitting in group 2. It's only got 2 electrons in its outermost energy level. Okay? To get a full outermost energy level, it needs to get to 8. So, theoretically, magnesium needs to gain 6 electrons. Sure, that's difficult in the world of chemistry, in the world of the atom. But there's a plan B that magnesium has. He doesn't have to go out there searching for 6 electrons. What he can say is, let me be clever now. If I've got 2 electrons there, it might be easier for me to lose 2 electrons. And if I lose 2 electrons, I'm going to go backwards. I'll go 1 and backwards 2, and I can get to the electron structure of neon. And isn't the electron structure of neon a completely filled outermost energy level? It is. So therefore, if it loses 2, okay, it's also going to have a valency of 2 because it's now lost 2 electrons to achieve its most stable state. Now, valency, what is it? It's basically how many electrons an atom can gain if it wants to gain, or how many, let me say that again. How many electrons it wants to gain, or how many electrons it wants to lose to achieve a completely filled outermost energy level. Okay, and in this case, the number of valence electrons and the valency is actually the same. And a very easy rule to remember is if you look at metals and non-metals, metals will always have the valency of their group number. Non-metals will always have the valency depending on how many hops it have to make to get to group 8. So what we have is valency of 3, 2, and 1. So we start at group 5. It needs 1, 2, 3. Whoopsie, went down a little bit. I'm going to leave group 4 out. Group 4 has got a couple of funny little rules. So I'm not going to get too worried about group 4. But if we go to group 3 will go 1, 2, and back over here, 3. It will lose. So non-metals will look to gain electrons, to receive electrons. Metals will look to get rid of electrons to get their outermost energy levels full. And cool. I think that pretty much tells the difference between valence electrons and valency.
Fantastic. I think we've got about 5 minutes left to the show, guys. There's quite a few questions on the page.
Sure.
So maybe, Bruce, if you're game.
I'm quite happy to take questions.
Okay,
yeah,
okay.
Absolutely.
Okay, so ready for the next 5 minutes, guys. Guys, if there's anything that you're not understanding with regards to this topic, please send it in now and we'll try and get through them. If we don't, please check back on the page within 2 days and we'll try have everything written back to and explained for you guys. Yeah, so just bear in mind that there's only 2 hands typing behind here at this very point in time. Okay.
And you've got to sprout another arm.
I know, or 5. Let's have a look here. There's quite a few. Khomotso, who's been asking such fantastic questions. Cool. I'm not too sure. It could have been with the last question you asked. She wanted to know, won't electron negativity affect the bonding hydrogen and fluorine?
Okay, we are in an area we haven't really touched on yet. Electronegativity is done a little bit later once you've looked at the bonding models. It is a very important concept. It allows us to determine what is called molecular polarity. Okay, now electronegativity will allow us also to predict whether we have a covalent type bond or what we have an ionic type bond. I know I'm using words now I haven't used, and that comes up a little bit later, but maybe in grade 10 you've spoken about those, which is great, covalent and ionic bonds. I'm not going to go too much down the road. I don't want to get into the concept of electronegativity just yet. We need to create a few more platforms before we get to that.
That's okay, Bruce. Like I said before, you must just tell me if we're jumping ahead.
Okay.
Because sometimes as mindsetters we do jump slightly ahead, and that's okay. That's okay because different schools are teaching different things at different times.
Absolutely,
so one step at a time, guys. Let's have a look. Let's see. Akim Banda wants to know why lithium is in group 7 of the periodic table.
Lithium?
Question mark. Yes.
Lithium.
Why
There's
is
lithium over here. Lithium's in group 1.
You see?
Not in group 7.
Hey, Akim.
Okay. So I don't know, are you getting confused with something else over here?
Perhaps.
Because if we look at group 7, it's fluorine, chlorine, bromine, and iodine. And if you go down to the others, well, I'm not going to worry about them. But fluorine, chlorine, and bromine, those are group 7s. Lithium is in group number 1. Okay.
Incredible. Yeah, well,
Sorry about that.
That was a quick answer. Tapiwa, let's have a look. I want to know about the oxidation number after the bond of hydrogen and fluorine. Is that also...
The oxidations we'll talk about a
Yes.
little bit later.
That's okay. So there you go. Tapiwa, oxidation
Okay.
later. Noka, when do you use the rule of 8 group number from group 5 to 8? And when do you use a group number as it is?
That's now that's what I spoke about a bit earlier. We use that rule of 8, in other words, to get that full outermost energy level of 8 electrons. We always use group 5, 6, and 7 to say we will gain electrons. Electrons will be gained into that. Okay, so in other words, the rule of 8 simply means how do we get a completely filled outermost energy level of 8 electrons. All right? So if we take group 5 will gain 3, group 6 will gain 2, group 7 will gain 1. So therefore we call those the valencies, as I spoke about earlier. The metals, which are groups 1, 2, and 3, okay? 1, 2, and 3. There, the group number indicates how many electrons the atoms will donate or give up to get the rule of 8 law obeyed. Because if you have a look at it, if I take electrons away, I will then have the same number of electrons as neon. Now, neon's in group 8. Neon has got a maximum or filled outermost energy level. So groups 1, 2, and 3, there you will lose electrons. So the group number represents the number of electrons that will be lost. And groups 5, 6, and 7, we have to add to get 8. So 5 plus 3 is 8. 6 plus 2 is 8. 7 plus 1 is going to be 8.
Fantastic.
Okay.
Bruce, you'll
Right.
never believe this, but we've got literally a minute and a half left.
Sure, time flies when you're having fun, eh?
I know, I'm telling you. Okay, I think this hopefully is a short one. Kuketso, let's see, 2 minutes. Why is
Cool.
helium in the noble gases group, but it doesn't have 8 valence electrons?
Now that is a good question. And I wish I had
Kuketso!
2 minutes for that, not 1. That's a great question. Why does helium does not have 8. It's only got 2 electrons. But remember, guys, and the quickest, easiest answer for this, it's in energy level 1. I shall rather say helium has got electrons. It's 2 electrons in energy level 1. What is the maximum number of electrons allowed in energy level 1? 2. So that fills energy level number 1. So even though helium is in group 8, it represents a filled outermost energy level. That's the only reason why it's there. It shouldn't be there for any other reason except that. And that's why the scientists have put it over there to represent a full outermost energy level. That's the answer.
That was fantastic. And you did it in 1.5 minutes.
1.5.
Well done, Bruce.
Oh, okay, there we go.
Guys, grade 11s, thank you so much. Grade 12s, don't you leave because you're on next. Grade 11s, thank you so much and join us next week. Bye.